let's do some examples. Here we can see that if we approach -2 with x, we end up with the denominator equaling 0, which is not something we would like. What can we do to get around this? Can we factor this? The top is x plus 2 multiplied by x squared and minus 1. And the bottom, we have, x squared plus x minus 2. Okay, minus 2. That means we're looking at some combination between 1, 2, and a negative sign. And how can we get that to add up to plus 1? X minus 1, x plus 2. I wonder how this will factor. So, this whole thing is equal to the limit of this straight line. Please note that if you take limit of something, you don't put limit of x plus 1. You put bracket x plus 1 other bracket, or left bracket, right bracket. You need to make sure, just like we say logarithms, you don't go, oh, log of x plus a. No, you put log of left bracket x plus a right bracket. You make sure your audience or your teacher knows what you're doing. Although I think I might be expounding this a little bit too much. So now that we're down to a polynomial, we apply the rule above, which was that, hey, polynomials themselves have no discontinuities. It's only when it's rational expressions that we can have discontinuities like this. Or, what else? We might have a piecewise function, which we'll see an example of in a moment. So this is -1. So with polynomials, we just substitute right in and evaluate. With piecewise functions, though, well, it's a little bit different. So here we're sending a package. Sketch a graph to represent this situation. Notice the emphasis I put on sketch. This, unless it's a computerized assignment, in which case you should probably use a computer. This, if it's done on paper, strongly implies that you do not have to be an artist of, say, Da Vinci's caliber to do this. Your diagrams should be at least approximately to scale. You should use a ruler to draw this, but you should not expect it to be perfect, especially if your medium is as horrible as this equipment is at sketching. So, over 500 grams, 1050. So 100 grams or less, 100 grams up to and including 200. 200 up to and including 500. So and this is 0. This is weight in grams. And this is cost in dollars. Always label your axes. So for 100 grams or less, it's $2, but we need to scale this thing for 10, a little bit over 10. So 2.00, and then 3.25 is going to be up here about. So this is over 100 grams. That means at this side you need to put a little bubble for excluded, and on the other end it's going to be the solid ball of inclusive. And why is there a dashed line here? It's because when people are sketching, it can sometimes be a little bit hard to tell, do these actually line up perfectly, or are they supposed to line up? If they're not supposed to line up, is there a gap in the middle where there's no value? So hence why the dashed lines. And over 200 up to and including 500 is 625. That would be up to about there. And 1050 would be about up here. Now, there are some very good reasons for the invention of graphing technology. Probably one of them may have been related to the fact that artists and mathematicians, well, the overlap is not as much as many people would like. So, wait a second. What should we put for the rest of over 500 grams? By the way, it may surprise you to know that this type of step function is described as left continuous. Why? It's because coming from the left, you can reach a value, a certain value, this threshold value, before you jump. Whereas coming from the right, you never reach that value before you have to jump down. So this is left continuous. What type of function is this? It is discontinuous. It is piecewise. And it is a step function. Discontinuous is because the limits do not exist at certain values. And what does that tell us? That tells us that at the left side and the right side, we approach different values. Now, given that the limit has to be the same on both sides, and it has to be equal to the actual value there for it to be continuous, that tells us limits make this discontinuous. So, how do we express this? Did we specify a variable? No. We just drew the diagram. Okay. So, what can we say? Limits at 100 grams, 200 grams, and 500 grams are, well, there's a whole bunch of words we can use. So, don't exist, or we might write something else, like say, oh, are disjoint. Or we could describe one of these other descriptors. So piecewise. Well, over different domains, we define this function differently. It's a step function because, well, we have a number of different constants that are used in piecewise fashion. So a step function is a special form of piecewise function where every single piece is flat. So it's a constant function. Where is a graph discontinuous? What type of discontinuity does it have? Well, there are three types of common discontinuity. We have jump discontinuity, at 100, 200, and 500 grams along weight axis. Because we didn't say, oh, let this be the W axis. Or we would have written W equals 100, W equals 200, W equals 500. What other types of discontinuity could we have had? Well, we could have had removable, like say, oh, like this, or like this. So just a point, or a point that's been moved somewhere else. Or we could have, well, obviously we can have a big gap. Okay, that works. So like say, oh, just nothing specified in between these. Okay, what others could we do? Okay, obviously there's some variation here. We could have both sides inclusive, both sides exclusive, or one inclusive, one exclusive, and switch around. Or, well, we could have infinite discontinuity, where we say have 1 over x squared. I mean, yeah, the limits approach positive infinity from either side, but it's still discontinuous because, well, you never reach it. Or something like that. Or tan of x. Try plotting tan of x. You'll notice that it has infinite discontinuities. And I don't mean an infinitely large number of them. I mean the type of discontinuity. Okay. Here we have another example. Evaluate this. What can we do here? Okay, we end up with 0 on top and 0 on the bottom. That's going to be a problem. So what can we do instead? Well, we could perhaps get rid of this square root somehow on top. Perhaps by multiplying by something. But then we would have a square root on the bottom. How do we deal with that? Well, we need to make sure that whatever we're multiplying by is not 0. Why? Guys. If whatever we're multiplying by is not 0, and if we can get the x's to cancel out, then we would have 1 over something, or something over something else. And hopefully it won't be 0 over 0. Okay, so x plus 81 root minus 9 times x plus 81 plus 9. This is over x times root x plus 81 plus 9. You see where this is going? Okay. We end up with limit as x approaches 0 of x plus 81 minus 81 over x times root x plus 81 plus 9. Now, as we can see, we can cancel these two out. We can also cancel the x and this x. Well, okay. X's are not very easy to cancel for a particular obvious reason. So, we end up with limit of x approaches 0 of, so this is going to end up being 1 over root x plus 81 plus 9. Now, for fractions, they are their own bracket. We do not need to go say, oh, lim of x plus 1 bracketed. Because, well, why isn't it lim of x? And then plus 1 tagged at the end. Okay. Here, what happens when x approaches 0? 0 plus 81 square root plus 9. And this leads us to 1 over 18. We don't use the negative square root interpretation here. Alright. So, what other concepts are there to think of when we're talking about limits? Okay, suppose that f of x is greater than or equal to g of x is greater than or equal to h of x for all x in some open interval containing c, except maybe at x equals c itself. Why? Well, at x equals c, say g of x has a removable discontinuity. So say f of x g of x and h of x. What happens when we pinch f of x and h of x together? Well, g of x gets squished in between. So, except maybe at x equals c itself. That means maybe we have a discontinuity here. Okay, so if we have a removable discontinuity here, does it matter for the limit? No. So, the limit is going to be somewhere between the limit for f of x and the limit for h of x. Or more specifically, it's going to be somewhere between the limit for f of x as x approaches c and for h of x as x approaches c. So if these two happen to be equal, what happens to g of x? It gets squished right in the middle. It doesn't necessarily have to have this shape. This is just a diagram. So if they're equal, then g of x gets squashed in the middle. Sure, okay, we might have a removable discontinuity. Fine. Does that do anything to the limit? No. Which means that the limit here will have to be equal to the limits of those two, because it got squished in the middle. And that's why it's called the Sandwich Theorem sometimes. Varying sources will differ. Now the Inequality Theorem says that if f of x is larger than or equal to g of x for all x in some open interval containing c, except possibly at x equals c itself, so removable discontinuity insurance, pretty much, in word form. Great. And the limits of f of x and g of x both exist as x approaches c. Then the limit for f of x is going to be bigger than the limit for g of x, or equal to, as x approaches c. So in other words, imagine the sandwich theorem except one-sided and without the actual sandwiching, but just pushing down on g of x. Or, depending on circumstances, maybe pushing up on g of x. Well, that's the inequality theorem. Now the summary, well, due to the large number of concepts listed in the section, please go back and look over the lists. Wait a second. Hey, if all the concepts there were basically what we would have listed in the summary if there weren't just so many of them, why did we talk a little bit about the types of discontinuity and then stop talking about them? Well, that's because next section we're going to talk more about continuity.